So today we're going to be looking at the beginning of Unit 3, which is all about scatter plots, or as we sometimes call them, scatter diagrams. And today we're going to do a bunch of things that you guys should have seen before. So first and foremost, what is a scatter plot, or sometimes we call it a scatter diagram? A scatter plot or a scatter diagram is a graph in which data pairs are plotted as individual points on a grid with a horizontal axis called your x and your vertical axis called y. It is very important when we make these to actually label your axes. So on this example, we have the wind speed for your x, and then we have drift rate for your y. A couple things I'm going to point out about the graph. First, notice on how all of these points are just points. Remember, with a scatter plot or a scatter diagram, we just plot the points. We do not connect. Never connect. Other thing, we mentioned this before, but right here, there is this little heartbeat part that tells us that we squished the graph together. That is why we are not starting at 0 or 10 or something here on our x-axis. Just like the other graphs, we need to make sure everything is equally spaced out, so that way our graph is not skewed and our graph is not misleading. Then we have our variables. We have our explanatory variable and our response variable. Our explanatory variable is the x variable, aka the variable that affects the other. Our response variable then is our y variable. So let's look at an example. So example 1. How much should a healthy Shetland pony weigh? Let x be the age of the pony in months, and let y be the average weight of the pony in kilograms. For the following information, the following information is based on the data taken from the Merit Veterinary Manual, in which most veterinarian colleges uses. A lot of times, if we're checking for validity of problems, we always want to see the sources. So we have this table, we have x, these, y, those points. So then what is the explanatory variable? Remember, explanatory variable is the x, and it says let x be the age of the ponies in months. Okay. And the response variable, remember, is our y, and it says the average weight of the pony. So then we're going to make the scatter diagram. We're going to draw our L graph, and then we're going to label our axes. So I know my x-axis, the horizontal, is our age, and our y-axis is our weight. Because our weights or our ages are so small, I'm just going to start off counting by threes. And then for our y values, we could do the heartbeat thing, but I'm going to, I'll count by tens. And I'll just interspersingly put numbers. So that way I know I'm counting by tens. And now I'm just plotting the points. So the first one said 360. So put a point. 695. 12, 140. 18, 170. And 24, 185. I'm not, once again, connecting the points because this is a scatter diagram. Okay. The other thing that we're going to talk about is correlation. Correlation is the mutual relationship or connection between two or more things. In scatter diagrams or scatter plots, we're always going to have it just be two things. So we're going to see on how well these two things are related, how well the explanatory variable affects the response variable. But there are different types of correlations. We have always known linear. Linear correlation forms a line. We found that out in algebra. So a rough diagram of it, you can see a clear line being formed. So that'd be a linear correlation. And that's our main focus, but we do need to be able to identify these other types. Exponential, just like how we looked at in algebra, forms a curve. So the curve could either start off going slow and then shoot up, or it could dramatically shoot down and slow off. These are examples of exponential. And then quadratic forms a U. Could either look like that or an upside down one. All three of these words, linear, exponential, quadratic, we looked at in algebra. So the word shouldn't be new, but this is a refresher of what it could look like. So, correlation coefficient. Correlation coefficient is a mathematical measurement that describes the strength of linear correlation between two variables. Key thing, linear correlation. It has to be a linear correlation to get a correlation coefficient. If it isn't, we can't do it. Now, just like all of our other measurements or our other processes up to this point, your calculator will do it for you. So off to the side is our steps for the calculator. And since we're using the calculators on the graphing on the Chromebook, we need to do this process every single time. So you need to hit second and then go hit 0. Then go to where it says diagnostic on, then hit enter, enter. These first 2 steps, you only have to do when you turn on your calculator. Every single time you turn on your graphing calculator and you're going to find your correlation coefficient, do these first 2 steps. Once you do these first 2 steps, you do not have to do them again unless you close your calculator and bring it back up. Next, you hit stat, then you hit enter. And just like before in unit 2, we're going to move up, hit clear, move down. But we need to do this for both L1 and L2, or list 1 and list 2. Then we're going to enter the data in both list 1 and list 2, making sure to hit enter after each number, and making sure that these show up as our points. Then we're going to hit second and mode to quit out. We're going to hit stat, move over, go down to where it says linreg, or linear regression, where it says ax plus b. Hit enter, go to calculate, and enter. Now, before we look at an example, we do need to understand the correlation strengths. So, for correlation strengths, it will always be a number between -1 and +1. So I have kind of a number line. Now, your number line on your notes only has a -1, the 0, and the 1. I would please add in the -0.75, -0.5, -0.25, 0.25, 0.5, and 0.75, because these are our dividers for strength. If the number that the calculator spits out is equal to -1, that is what we call a perfect negative linear correlation. It perfectly forms a line. So if it's equal to -1, it's a perfect negative linear correlation. If it is between -0.75 and -1, we call it a strong negative linear correlation. Negative because it is a negative number, and also the graph looks like it is going down. If it's between -0.5 and -0.75, it's a moderate negative linear correlation. If it's between -0.25 and -0.5, it's a weak negative linear correlation. If it's between -0.25 and +0.25, so in this range, it is no linear correlation, meaning it is so spread out it doesn't look like it forms a line. So remember, each of these tells you on how close these points make a line. So weak is kind of spread out, moderate getting closer, strong getting even closer, linear, or perfect being a perfect line. Now in reverse, positive 0.25 to positive 0.5 would be a weak positive linear correlation. Between 0.5 and 0.75 is a moderate positive linear correlation. Between 0.75 and 1, it is a strong positive linear correlation. And if it is equal to 1, it is a perfect positive linear correlation. So we have 2 more examples to look at. Example 2. In baseball, is there a linear correlation between batting average and home run percentage? Let X represent the batting average of a professional baseball player, and let Y represent the player's home run percentage. A random sample of 7 baseball players gave the following information. So once again, explanatory variable is our X, or our explanatory, which in this case is batting average. Our response variable is our player's home run percentage. And now we need the correlation coefficient. So we need our calculator. So first thing we need to do, since you pulled up a calculator, we need to hit second 0, and then we can hit up, go down to diagnostic on, and this is in alphabetical order, so use a little bit of logic to find out where it is. So diagnostic on, we'll hit enter, and we'll hit enter. Next, I'm going to hit stat, hit enter. And I don't have anything in my list, so I'm not going to move up and hit clear and move down. If I did, I would. So now I'm going to enter my numbers. I'm going to go in the same order for my list 1 and list 2. So 0.24, enter, 0.26, 0.28, 0.26, 0.27, 0.33, and 0.29. So I just went left to right. I'm going to hit over to get to list 2 and put in the numbers. So 1.4, 3.6, 5.5, 3.8, 3.5, 7.3, 5.0. Then it said hit second mode. I'm going to hit stat, move over to calc. I'm going to move down to number 4 where it says lin reg ax plus b. Enter. Go down to calc and hit enter. Okay. I'm going to talk about the top 3 lines in the second guided notes for unit 3. But what we need is this R. The R value is our correlation coefficient. So our R is 0.95. So that tells me that that falls between the 0.75 and the 1. So that is a strong positive linear correlation. You will need all 4 of those words to correctly answer that problem. Strength, positive or negative, linear correlation. Go ahead and take a moment and draw your scatter plot. And let's see what you get. This is what I ended up getting for my scatter plot. For my x's, I counted by 0.05s. For my y's, I counted by 0.5. Now I just put in my dots. Once again, I did not connect them. For example 3, it says identify the correlation shown below as either no correlation, linear, exponential, or quadratic. The correlation is linear. Determine if it is a perfect, strong, moderate, or weak. So go ahead and take a moment and try to identify all 6 of these. This is what I ended up getting. First, I said a weak negative linear. I know it's linear. I'll kind of cheat. I put in a line. But it looks like a general line going down. And because it's going down, it's negative. Now I said weak because these points are rather spread out and not close to the line. Second one I said is quadratic because it forms a U. Third one I said a moderate positive linear. Positive because it's going up, linear because it looks like it forms a line, moderate because it's getting pretty close. If you said strong, I would accept that also. Bottom left, I said exponential because it looks like it starts at slow and then shoots up into a curve. This one is a perfect positive linear correlation. It's perfect because all of these points are on the line. And this last one is a no correlation because it looks like it's just all over the place. It doesn't form a U, it doesn't form a curve, it doesn't form a line.